still getting the hang on the live stream stuff. It's just, I have a PhD in mathematical statistics, and I can't get this damn live streaming software to work, and yet somehow 16-year-olds manage to figure out how to live stream playing computationally intensive video games. It's funny how technology can humble you. So I'm doing this live stream on applied probabilistic modeling, hoping to do this once a week, Monday at 3 p.m. 11 a.m. Eastern. Today, I want to run through this. Hold on, I got this clicky keyboard here. I want to run through this, an intro to Julia. So Julia is a programming language with used in data science and machine learning, and there's several really interesting probabilistic programming languages implemented in this language. Oh, it's dark. Dark. Let me get some light. Ooh. All right. Yeah, there's some good probabilistic programming languages implemented in Julia, and so I'm kind of dabbled in Julia before, but I want to go through an intro again. So I'm hoping that I can get this kind of set up such that I can run through a nice. I can get up to speed on some Julia probabilistic programming in the next live stream. I'm gonna play some music, man. I like coding with some music. I don't know, what could I play here? I got Spotify hooked up to this my sound output here. Let me see if I can't play some. I want to play some Christmas music. Oh, and Spotify crashed. Don't understand. Oh, whoa, there we go. Turn that volume down. There we go, that's good. Don't want it too loud. All right, some Christmas music. Coding Christmas music. Let's go to, so this is a course they actually have on the Julia website. I think I'm already enrolled. Let me go to it. All right, so welcome. Hopefully I can just run through this. And no sound, wait 1 second.
Hey everyone, and welcome to the Julia language. For those of you who are not familiar, Julia is a new, general-purpose, high-performance programming language with the tagline, looks like Python, feels like Lisp, and runs like C or Fortran.
That's cool.
The point is that Julia is easy to use, powerful, and extremely performant, all at once. Thank you so much for coming to check out the channel, and we hope that you enjoy it.
All right. I like that idea of it looking like Python and feeling like Lisp. Okay, so install Julia and interact.
Hey everyone, how's it going? My name is Logan Kilpatrick and I'm the community manager for the Julia language. In this video, we are going to be going over how to actually install Julia locally and then how to also install Interact, which is a software that's going to help us run notebooks in Julia. So step one for this is going to be going to the Interact website. The URL for the website is just interact.io. We can click try the Interact desktop app for Mac OS or for Windows or whatever your operating system is. So we'll give this button a click. It is going to open up a downloader. Once this finishes downloading, we're just going to give it a double click.
Still downloading.
This process might look slightly different depending on what your operating system is.
It's taking a long time to do.
I'm running on Mac OS, so it looks this way on Mac OS, and like I said, it might look slightly different for you depending on if you're running Windows or Linux. So we see the little interact icon. Just going to drag that into the application folder. And that gives us step 1 is complete. So we have interact installed on our computer now. Step 2 is actually going to be to install Julia locally on your computer. So you can open up another tab, and we are going to go to julialang.org. The website might look slightly different depending on when you're viewing this video, but as of this moment, this is what the website looks like. So we're going to click on download in the top left-hand corner. The current stable release of Julia as of the recording of this video is Julia 1.4.1, and all of the lecture materials for the Introduction to Julia course that you're part of will all work with Julia 1.4.1. So I'm running on Mac OS, so I'm just going to click the 64-bit download for Mac OS. It's going to open up a downloader just like it did before for Interact, but this time for Julia. Two-finger click that again, or double-click that again, rather. And again, this process will be slightly different depending on what your operating system is, but in general, this is the steps that you're going to want to go through. So we have the Julia 1.4 application. We're going to drag that into our application folder. It moves everything over. We can clear all this out. So the very last installation step that we're going to have to do is you're going to see Julia 1.4 here in my applications folder. I have a bunch of other versions of Julia because I've done Julia development in other versions of Julia. But for this video, we're going to be using Julia 1.4. So for me on Mac OS, I'm going to two-finger click the icon, and I'm going to click Open. This is going to open up Julia in my terminal. It's going to ask me if I really want to open it up, and I do really want to open it up, so it should pop open. And this is what the Julia in your terminal will look like by default. All I want to do now, the very last step to connect Interact and Julia together is installing a package called iJulia. So you see the little bracket icon in between these quotation marks. You are going to want to type that into the Julia terminal. So without the quotation marks. So I'm just going to type that in. It's going to show at v1.4 or whatever version it is, and then the word package. So after that, you're just going to type add iJulia. And this will add the iJulia package. Again, iJulia is just sort of an interface between the Julia language itself and the Interact application on your computer. So you need this as sort of the intermediary between these two pieces of software. So you can see it says resolving package versions here. My project.toml and manifest.toml files didn't change. I actually had Julia previously installed on my computer. I just removed it and then reinstalled it for this video. So in your case, it might not look exactly the same, but the steps are exactly the same. You're going to add iJulia, and then you'll see a bunch of stuff show up on the screen, and it might do a bunch of other printouts. But this is the only step that you need to actually do in the terminal. So don't worry if it looks a little bit different on your computer. So we have iJulia installed, which is awesome. Next, we're going to want to actually go and launch Interact and make sure that everything worked the way that it was supposed to. So for me on Mac OS, I'm going to navigate back to my applications folder. I'm going to find Interact. Here it is. And I'm going to open it up. So it's probably going to give me a warning here. And it's going to say exactly. So it's saying Interact can't be opened because Apple cannot check for malicious software. This is totally okay. And this is what happens if you double click to open up the application after you install it on newer versions of Mac OS. To get around this, you can just two-finger click or right click if you're using a mouse, or control click. and then press
so this
open.
is a bit tedious. I'm trying to install
And then,
these.
yes, I really do want to open it. I'm pretty sure that's a operating system specific quirk, so you won't have to do that if you're running on Windows. So now we have a blank notebook open. The only thing we want to check really quickly is on the toolbar at the very top of your computer, it should say Runtime. You can click Runtime, and then we want to make sure that near the bottom it should say Julia 1.4.1. So as long as it says that, that means that we are good to go. So mine says Julia 1.4.1 because I installed iJulia and all of that worked, so I'm good. I can close this out, and now we can navigate back to the tab that had Julia Academy open. And you can see this is what the course looks like. We see Jane's awesome video here. And then there should actually be some download buttons that include some files, and the files end with .ipynb. And that is just the standard extension of a notebook file. So we can give that a click. It's going to open the file up again. I can double click to open that file. And now we see that we have this notebook open that Jane is going through in her examples. So we can then go cell up in the top left-hand corner, and then we can do run all. And what that's going to do is that's going to run each individual cell of this notebook. And if you look closely where my cursor is right here, you'll see that it's about to.
This is a nice setup. My only problem is
I
can't get these damn files to load. It might be that I wonder if there's a way. Like I'm trying to open the DMG files for either of these files that I just downloaded. It's not seem to want to let me do that. I don't know why. Okay. I mean, is there an online editor? Also, online Julia Interact. There we go. Why gotta sign up? Everybody's wanting you to sign up. All right, so how am I going to run these both at the same time? Let's see here. My guess is that if it requires me installing libraries, we're going to have problems. Let's see if I can't replace my terminal with this new window. Something. All right, let's try that. All right, so hopefully we're in a place where we can do something. I'm having trouble installing these files. I don't want to bore you with that process, so let's jump right into. We got a notebook here. Well, let's just kind of look off her video, see if we can.
And here we go. All right, so in this first notebook, I'll show you a few basics, just like printing to standard out, variable assignment, commenting, and syntax for basic math operations. So in Julia, we usually use the println line to print. If you're new to Jupyter Notebooks, there are a few different ways that you can execute a cell. After you've selected the cell, you can hit Shift and Enter to run the cell. Alternatively, you can use this Run button, the arrow up here. And if you're interested in running multiple cells at once, you can go to Cell from this drop-down menu and choose, for example, Run All or Run all of the cells below. By default, in a Jupyter Notebook, when you execute a cell, the last line of the cell will print a standard out. And if you're interested in suppressing that output, that's when you can add a semicolon.
Very Pythonic.
So assigning variables. In Julia, we don't need to explicitly state a variable's type when we declare it. So we see here that we're assigning my answer to 42. We have a variable called myPie and then a variable called myName. And Julia figures out the types for us. So Julia understands that 42 is an integer, that pi is a float, and that Jane is a string. After assigning a value to a variable, we can reassign another value of a different type to that same variable without any issue. So my answer used to be an integer, but I'm able to reassign it to my name, and now we see that the type of my answer is a string. If you want to comment when you're in Julia or a Jupyter notebook, you can use just a # for a single line comment. And if you're interested in a multi-line comment, you can do # =# where your comment is placed between those two equal signs.
I'm going to shuffle this view around a little bit.
So the syntax for basic math operations will probably be pretty straightforward to most of you. We have addition, subtraction, multiplication, division. Probably the most notable thing if you're coming from a Python background is that to exponentiate, you're going to use this caret.
Could use a what? What happened? We ran out here.
So now I'll head back to our directory and go to the second notebook on strings. So in this notebook, we're going to see how to create strings and then how to interpolate and concatenate variables into a string, or to evaluate expressions within a string. So in this example, I declare a few variables called name, numFingers, numToes, and in this first call to print ln, I throw a $sign next to name. In the second call, we have a $sign next to numFingers, one next to numToes here, and then also one next to this expression enclosed in parentheses where we're adding numFingers and numToes. So if we execute this cell, we see that Julia correctly inserts Jane, 10, 10, and then adds 10 and 10 to get 20, telling us that I have 20 digits in all. Okay, so our final section on strings is on concatenation, and I'll show you 3 different ways to concatenate strings in Julia. The first is to use this string function. This takes an arbitrary number of arguments, and we can use it both to concatenate string literals and to convert non-string values to strings. So in this first example, we throw 2 string literals together to get the string how many cats are too many cats. And in this second call to string, we throw in 2 string literals and then an integer to get a single string. I don't know, but 10 are too few. Alternatively, we could have used this multiplication or star operator to adjoin these 2 strings. So here I call the same strings from that first example S3 and S4. And if we just multiply them together, we get a single string. We could have also used string interpolation just to insert these 2 strings into a single set of quotation marks.
This REPL is super slow. Shoot. Just skipping ahead. All right, I'm just going to just assume that I'll figure strings out. What was the bit? There was something in there.
So specifically in this notebook, we're going to do an overview of dictionaries, tuples, and arrays in Julia. And for those of you that are less familiar, an overview of sort of the major differences between these data structures is that tuples and arrays both contain ordered sequences of elements, whereas dictionaries are not ordered. And then, unlike dictionaries and arrays, tuples are immutable, so that means that we can't change their contents once they've been declared. So we'll start off here with dictionaries. To create a dictionary, you can use this dict keyword, and you have the option to include information for your entries in the parentheses that follow the dict keyword, or you can just add your entries later after simply initializing an empty dictionary. So the syntax for adding key value pairs as you initialize the dictionary is to type the key, followed by an arrow sign that's composed of the equal sign and then the arrow pointing right, and then you follow that with the actual value. So we can see that here I'm constructing a dictionary called My Phone Book, and I've got just 2 phone numbers in here, Jenny and Ghostbusters. So we can run this, build our dictionary. And if we now want to add additional entries to this existing dictionary, we can assign a value to the name of the dictionary, followed by a set of square brackets, where within the square brackets we enclose the key of the new entry that we're aiming to add. So in this case, our new key is Kramer, and the value associated with Kramer is his phone number, 555-FILK. And so we add to our dictionary that way.
Is that a new item?
And now if we execute this line that says my phone book, we should see our new dictionary, or our updated dictionary, which now has 3 different entries. So we see that adding this third entry worked. Now if we want to grab the value associated with a particular key, we can use the same syntax that we used to add a new key value pair to our dictionary, just to grab the value associated with this key. So if we scroll down here, we see, again, we have the name of the dictionary followed by square brackets, and then the key enclosed within those square brackets. So we do that, and we return the value associated with Kramer, our
What's
key.
the print thing again? So just...
We can use the pop function to delete a key of interest from a dictionary and simultaneously return the value that was associated with that key. So here, if we want to delete Kramer now from our phone book, we feed to pop the name of the dictionary that we're trying to alter, and then the key that we are wishing to delete. And now if we run our phone book again to see what it looks like, we see that we only have 2 entries remaining. Now finally, because dictionaries are not ordered, unlike tuples and arrays, we're not able to index into them. So if we try to use like typical indexing syntax.
All right, so bit of a pause here. I'm trying to kind of work through this. This introduction to Julia, and using this, couldn't get for some reason, installing Julia while doing other things was causing issues. So I'm trying to here just kind of use this online REPL, which is not that great. But anyway, so I'm trying to print. How do you print? Is it print line? Is that not a thing? That was what we just learned. This thing. Don't like it. Oh, why is it showing me the entire history of the comic? Not ideal. Okay, so let's see here. Doesn't like that method. How do you? All right, fine. The Julia print item. Okay. Let's see. Yeah, I'm gonna have to be careful with that arbitrary Google searching. Not sure how, or at least I should put safe search on strict. So what is this? Something imports base dot show. I should just work from this thing. All right. Base dot show x. Well, that's nicer. Let's just do that. Can we just do import base dot show as show? Is that a thing? Then that'd be too much to ask. Does show just work by itself? Yes. Show x. Awesome. All right. So what do we miss here? So we got our dictionary, and we can say we got x. X equals, what do we do? Z equals 3. Can we do some overwriting? My favorite one of these songs is yeah, this is King Wenceslas. King Wenceslas is nice. Let's start that over. King Wenceslas. Why I learned about dictionaries. That's not Wenceslas. Let's came down on the feast of Stephen. I don't like these verbose messages. Come on. Yeah. Oh, what happened to Z? Okay. X. Let's try some overwriting. Bring me wine. Bring me wine monks hither. Thou and I will see him dine when we bear them thither. So okay, we can overwrite. And what was the last one? Or some poppy thing? Pop? I was using pop for something. Pop, bang, X. All right, that's cool.
Remaining. Now finally, because dictionaries are not ordered, unlike tuples and arrays, we're not able to index into them. So if we try to use like typical indexing syntax, Julia thinks that you're trying to look for a key called 1 here. Doesn't, yes, because dictionaries are not ordered. So now tuples. We create tuples by enclosing elements within parentheses.
Much like
so tuples are ordered, which means we can index into them. So in this case, I'm starting with a tuple called My Favorite Animals, which has a group of 3 strings. And if I throw the number 1 within a set of square brackets next to the name of this tuple, I should get the first element of that tuple. The reason being that Julia is 1 indexed rather than 0 indexed, so we start counting from 1.
It's an ordered tuple by default, okay.
Now, tuples are immutable, so that means that we can't update the tuple. So, if I were to try to reassign otters to the first element of this tuple, and to replace penguins with otters, I'll get an error. So we're not allowed to do that. I figure that's not really so bad, because if we had to pick penguins versus otters, there is a clear winner. And now we're on to arrays. So arrays are both mutable and ordered. So we can create an array by enclosing elements within square brackets. So in this first example, I'm creating an array of strings, and Julia correctly recognizes that this is an array of strings. In another example here, we have an array for the Fibonacci sequence, and this is Julia's way of telling us that this is an array. Particularly, it's a one-dimensional array of in64s. And we don't have to create arrays that have only the same element type. So if we wanted to make sort of a mixture, we're totally able to do that.
Oh, okay.
And what you'll see in that case is that the type of this one-dimensional array is just any. Okay, so we can index into arrays with square brackets the same way that we were able to do with tuples. So in this case, the third element of our last array, my friends, is Barney. And because, again, arrays are mutable, we're able to update the elements of that array with that same indexing scheme. So you can see now, if I call my friends again, So now our array has been altered to include Baby Bop instead of Barney. So we can add items to the array with the push function and take them away with the pop function. Both of these functions take the name of the array that we want to alter as the first input argument. Pop by default is just going to give you, it's going to pop off the last element of your array. Push is going to add an element to the end of the array, and you specify which element it is you want to add as the second input argument. So we can add 21 to our Fibonacci sequence, and here we see the updated array. Now if we wanted to remove it, pop will return the value that we are removing, and we can see now that our Fibonacci sequence has returned to its original state where 13 is the last entry. Okay, so far I've only just shown you one-dimensional arrays of scalars, but we can actually construct multi-dimensional arrays as well as arrays of other data structures. So favorites and numbers here are both arrays of arrays. And note that when you're creating an array of an array, you don't actually, so the arrays that are populating this array numbers don't have to all have the same length. They can be a very.
So it's checking in like so again, this is a live stream on probabilistic modeling, applied probabilistic modeling, and we got a whole bunch of interesting probabilistic programming languages in Julia. So I'm just going through the basics of acquainting myself with Julia before we get started on those things here. So we'll probably, when we exhaust the hour, we'll hopefully, I don't know if I'll get through all this, but I think these are all the important things. We can probably try and push through all this. But yeah, next time we'll definitely dive into some actual Julia probabilistic programming.
Variable length. And then using the rand function in these last two examples in this notebook, we can create two-dimensional, three-dimensional, arbitrarily dimensioned arrays. Rand will take an arbitrary number of arguments. And so in this case, when I call rand on 4, 3, this is saying that I want a two-dimensional array because I've passed two input arguments to it. I want the first dimension to be of length 4, the second dimension to be of length 3, and then by default, rand populates the data structure that it creates with random numbers between 0 and 1. And so then this call to rand tells us that we want a 4 by 3 by 2 array.
What are the characters that are used for strings? I think I used double quotes. It's a tried. Oh my god. You can use either, okay, this is the triple quotes. Let's try it for multi-line strings. All right. How do you access elements from a container at a given location? Boom. What is one large group of arrays in tuples? All elements of an array must be the same. What is a large difference? Oh, well, arrays are mutable, tuples aren't. There we go. Function push says what? Append something to an array? What are the characters that are used for strings? Why am I stuck in this purgatory of quiz questions here? What is one difference between arrays? Oh, all right. Can we go on now? Control. You can either download the notebook or...
Hour and a half. It was extended to 2 hours, but I had this open early this morning to...
That's not what I want. Sorry. Bum.
Hour and a half early this morning to make sure everything was in working order. Okay, so we're in our fourth notebook now, loops. In this notebook, we're going to talk about both while and for loops. Now the syntax for a while loop is to follow the while loop with a condition on the same line. Then on the next line, you start the loop body, and you want to terminate the while loop with an end keyword. So for example, we can use a while loop to count in this first example. We're just increasing n from 1 to 10 there. We can also use a while loop to iterate over an array. And we could do both of those things with for loops as well. So to write a for loop, we use typically the for, well, always the for, but typically the in keyword. And then you have some iterable object that, like an array or a range, and you assign a new value to this variable with every iteration of the loop. The loop body is then starting on the next line in this typical syntax for a for loop, and we end the for loop with the end keyword. So we have exactly.
So what have I done here? Unknown function. I think it's in like this. Is it not like print line? Is that a? No, what's the issue here? This is frustrating. Error during bootstrap. Pretty sure that was like verbatim what she typed at the beginning of this. N equals 0, while n is less than 10. Do I need to put some white space in here or what? So weird. Why? If I just do nothing, will it work? Okay. Will that work? Okay. Okay. So this, hold up. Still all this nonsense. Refresh it. Can I just if I just deal with the regular n equals 0. What the heck? N equals. Well, n. Oh my goodness. Plus equals 1. Okay, guys. It has. It's kind of like IPython that it has. Next line continuation. But we just defined that. Can I go up and redo stuff? The undefined variable area n is not defined. These are, I mean, I guess it's good that I'm hitting errors like this because it's kind of thing that you think you would probably need to sort out. It's kind of those weird things that languages do that you gotta kind of have to get out of the way first before you can do anything useful. I have no idea why this is not working. This seems pretty straightforward. I'm typing exactly what she has here. But what's all that? Jeez. All right. I can't even tell. Does it not like this print line? The errors are just terrible. I mean, unless it's some kind of weird environmental error that. Frustration. I guess we'll just have to watch what she does here and memorize. All right, so we got some while loops. While and with the close of an end. Looks like white space doesn't matter. There's no this. Well, I guess white space has to matter because there seems to be no kind of closing of this condition expression here, and the expression inside the while block is just kind of indicated by an indent. Man, I'm frustrated with all the technical issues. Oh, look, we got a REPL thing here. Well, let's try it here. I did not know you can import. Oh, I should do this. Well, my course has got some REPL editors here. All right, so literally the same technology. I don't know why it doesn't work. Over here. Click on play and fail. Oh, wait, what? Global. All right, I'm going to need you to explain what this global thing is doing. While condition, loop body, and for example. All right, so we're going to need you to talk about global. Miss, I'm sorry, I've forgotten your name.
In this first example, we're just increasing n.
I've seen globals in other languages.
1 to 10 there. We can also use a while loop to iterate over an array. And we could do both of those things with for loops as well. So to write a for loop, we use typically the for,
so
well,
like
always
syntax.
The for, but typically the in keyword. And then you have some iterable object that, like an array
See,
or
I can
range.
tell this is going to confuse me because this for loop is like a perfect mix of Python and R syntax, so that you always forget which one is which.
The loop body is then starting on the next line in this typical syntax for a for loop, and we end the for loop with the end keyword. So we have exactly, I guess, translations of the exact same loops that I did under the while loop section. So here we're just counting with the for loop from 1 to 10, and here we are iterating over the elements of an array. Now we have some flexibility with the syntax of a for loop, so we can change this in keyword to either an equal sign or to this is an element of sign, and we'll get the same result. So this is what counting looks like with the equal sign, and then
I don't even know how to write
counting
that.
with this is an element of sign.
You just like hold down E or something?
Okay, so in this next set of examples, we are going to use for loops to create some addition tables. So in these addition tables, the value of every entry of our 2D arrays or matrices will be the sum of its row and its column indices. So we start by initializing a 5x5 matrix or 2D array with zeros. That's what this zeros command does. So here is our matrix A. And then we're going to use this embedded for loop to populate A, entry by entry. Okay, so alternatively, we could have done the same thing by condensing this nested for loop, which we show here. So doing this to a different matrix, so I'm reinitializing. Now I have a matrix B, and now I'm populating B at every entry within the matrix in the same way that I did to A, except this double for loop is all on one line. We're iterating over both I and J here.
Let's look at it last time.
Now, the more
Equals
Julian
10.
way to create an addition table would be to use an array comprehension,
5.
as we do here when generating this matrix C. So in this case, we have the same components of our nested for loop, but they're arranged in a slightly different order, and inside a set of square brackets. So we should also note that in this third way of creating an addition table, we didn't actually have to pre-initialize the matrix C. We were just sort of building it from scratch as we were performing the array comprehension. So the last example in this notebook is just an array comprehension embedded in a for loop. And so the idea here is that this matrix A that we're creating on every iteration of the for loop is an addition table, but the size of that addition table is growing as we progress through the for loop. So we get a bunch of addition tables, increasing size. So that's the end of notebook 4.
So display is what then? Display is just a...
All right, so the keywords that you need to know to write a conditional statement in Julia are if, else, and end. And so an if statement looks like this. We have if followed by our first condition. If this first condition is true,
Okay,
we
that's
execute
pretty
the
straightforward.
body, which is normally starting on the next line. That's followed by, if you have additional conditions to consider, those conditions preceded by else if, and then the body of code that you want to execute if one of those other conditions is
What's
true.
display do instead of print?
And then you have the option to terminate the conditional statement with else, so you have a sort of a default option, which here is called option 3 and gets executed if none of these other conditions are true. You terminate, as with while and for loops, you terminate with an end statement.
Then we got for loops. Let's look at functions. This will probably be the most important thing. Then we'll figure out kind of how packages work. Plotting, I'm just going to...
All right, so the topics that we're going to cover in this notebook include how to declare a function, duck typing in Julia, mutating versus non-mutating functions, and then something called broadcasting that I'll explain when we get to that part. All right, so first we're going to show a few different ways to declare a function. Now the first way looks a bit similar to our for loops and our if clauses. We have a function keyword, we have the function body, and then we terminate with an end keyword. Now we follow the function keyword with the name of the function that we wish to declare, followed by a set of parentheses, and if applicable, we have the name of our keyword, or not our keyword, sorry, our input arguments given inside that set of parentheses. So this function here, we're declaring, called say hi, and it takes some variable and then greets the variable. And then the second function that we're declaring is f of x, and it squares its input. Now, alternatively, rather than using these function and end keywords, we could have declared either of these functions with simply one line of code. Oh, but first first I'm going to show you that we can call each of these functions. So we just pass one input argument to either of these, and we, as we would expect, get a string or the square of our input. Okay, so now I'll show you that we could have declared these same functions just using a single line of code. So the syntax for declaring a function in a single line is just to give the name of the function that you wish to declare, again followed by the set of input arguments enclosed in parentheses, and then in this case you just put the function body to the right of an equal sign. So here we have say hi to and f2, which do the same things as say hi and f. And just as before, we pass one input argument to either function and see that they execute just fine, as we would expect.
Okay.
Now finally, the third way to write a function that I'm going to show you today is to write anonymous or lambda functions. So in an anonymous function, we write our input variable, here our input variable's name, to the left of an arrow, where this arrow is created just by the dash and then the right pointing arrowhead. And to the right of that arrow, we put the function body. So we can kind of think of this lambda or anonymous function as a map that's taking inputs and mapping them to outputs. And then you have the option to assign to this lambda or anonymous function a variable. So in this case, I'm assigning the variable, say, hi3 to our anonymous function. And
it's like somebody came into my moment.
In this other example, I'm assigning the variable f3.
Yeah, so
and
I mean, just to summarize, I'm going over
different
this
from our other
intro
ways of creating functions.
Julia, because there's a whole bunch of
syntax
public
for
modeling
calling each of these
languages in
functions
Julia
looks the same.
that I'm going to go over in the
So we just enclose our input
coming,
arguments in parentheses next to our
so these are all
our functions, our function names, or the variables that
so yeah, it looks like next
are
time I'll
tied
dive into
to our
Turing.
lambda functions.
After that, I'll look at Gen, then Omega.
Now, Julia
I figured I
functions
was gonna
tend
blitz through all of
to
these-
work on whatever inputs make sense.
These Julia-based.
So previously we
probabilistic
called say
programming languages. See if
hi
we can't find some interesting
with a string as an input, but
examples
we
here.
just as easily could have given it an integer input.
duck typing.
So that function still works, and I leave to the viewer to look up or identify this TV character. And we see similarly that the function f is going to work on a matrix just as it worked on a scalar. So here we have a randomly populated 3x3 matrix, and when we call f on that matrix A, we get an output. Now the reason this works is, in the case of f, the reason that calling f on a matrix works is that all f does is square its input, and the square of a matrix is a well-defined operation. Now on the other hand, if we had tried to pass a vector or just a one-dimensional array to f, we would get an error, and I'll show you that now. So if we have some v, variable v, holding our one-dimensional array, and we call f on v, it gets unhappy, and the reason is that the square of a vector is not a well-defined operation, so it's ambiguous, like if you want the inner product or the outer product, and rather than taking a guess, we just have Julia return an error. So mutating versus non-mutating functions. Mutating functions are functions that return an altered version of the input that you pass to them, whereas non-mutating functions do not alter their inputs. So the convention in Julia is to follow the names of mutating functions with an exclamation mark or the bang sign.
So wait, okay, so that sounds like a bit of nuance we should capture.
And we call f on v, it gets unhappy, and the reason is that the square of a vector is not a well-defined operation, so it's ambiguous, like if you want the inner product or the outer product, and rather than taking a guess, we just have Julia return an error. So mutating versus non-mutating functions. Mutating functions are functions that return an altered version of the input that you pass to them, whereas non-mutating functions do not alter their inputs. So the convention in Julia is to follow the names of mutating functions with an exclamation mark or the bang sign, whereas functions that are lacking that bang sign are non-mutating. So an example of this is sort versus sort.
So it doesn't
sort bang, I should say. So here we have a one-dimensional array v that just has 3 elements, 3, 5, and 2. If we run sort on v, we get an output which is a sorted version of v. But if we look at what v is after calling sort, we see that v is what it was originally declared to be, just 3, 5, and 2. Now on the other hand, if we had called sort bang, we get the same output where we see a sorted version of v, but now if we look at the contents of v,
that's interesting.
We see
like
that v
I hate
matches the output of sort
both
bang
R and
v.
Python,
So
how
we've
mutation and non-mutation
v and using
just
a
mixed
mutating
together.
function.
You never know
And you
what's
might have
doing
noticed
what.
that there was an exclamation mark following the functions that we used in Notebook 3 on data structures for the push and the pop functions, with the reason being that we were passing an array to those functions, editing the array that we had passed as an input. And so those are both mutating functions as well. So final topic within this notebook 6 is broadcasting. So I'm going to explain what broadcasting is, but first we'll say in Julia, broadcasting behavior is denoted with a dot. And we place that dot between the function name and its list of input arguments. So in this case, the function f would be non-broadcasting, function f dot would be broadcasting.
Great.
And the difference between these two is that this regular function f, which is not broadcasting, if you pass it an array, it's going to treat that array like a single object and call f on that object as one piece. Whereas in the case of broadcasting, sort of the object that you pass it.
I'm going to guess what this is. Let's see if I can't. All right, so if I'm in a function f, which is just x, what was it? Could we just do that? Okay. All right, so we call f on 2. And so let's just try f dot 1, 2, 3, 4, 5. Great, that worked. Display x. Okay, so x, no zero indexing, 3, I don't know. Let's just check the guts here. Okay, cool.
Array, for example, is going to be sort of dissected, where f is going to be applied to every single element of that object rather than treating the object as a whole. So I'll show you an example of that now. So create another matrix that we're calling A. So the indices
wrapping
are
this
from
up.
1 to 9.
So yeah, just going through this quick
if we call
Julia
f of A,
tutorial,
recall that
so
f
that
was
next
just
time
taking
I
the
can hop
square of its
into
input.
this.
So this is the matrix
where
A
is it?
multiplied
This,
by the matrix A. Now on the other hand, if we call f dot A,
probabilistic programming languages implemented in Julia.
at every
so we got
entry
Turing,
of this
got
output
Gen,
matrix
got
B,
Omega.
we have the
There's a few
square
others that
of
I'm
the
missing.
entries
Figure may
that were
as well just
contained in
knock
this
out all
original
these
matrix
Julia
A.
languages
So for example,
in the series.
9 gets squared, and in this bottom right-hand corner,
compare
we
how
have
they feel
81
if you
in the broadcasted version.
know any other good languages.
Now, one thing
Julia
that's
space
important to
review,
note
let
about
me know.
this is that though f did not work on v, because we weren't able to just square, when we had a vector v, or a one-dimensional array v, we weren't able to square that vector because that wasn't a well-defined operation.
Yeah, we get it.
On the other
Okay.
hand, if we want to broadcast f over a one-dimensional array, that is a well-defined operation because it's unambiguous.
Cool. So let's wrap it up with these packages. So, packages would be useful to know.
All right. Okay, so at the time of this tutorial, Julia has 1,686 registered packages, so they're a pretty important part of the Julia ecosystem. Now, if you're interested in seeing all of Julia's available packages, you can go to one of the links provided here, either this package list here or Julia Observer. And I'm going to show you how to use a package, but this part doesn't perfectly translate from like a Julia installation on in your local environment to Julia Box. So we're not actually able to use this command, which I'll explain in a second, on Julia Box. But typically, when you're not on Julia Box, whenever you're using a package for the first time on a given Julia installation, you need to use the syntax package.add to explicitly add that package to your environment, where the name of the package they're adding is enclosed in quotation marks inside the parentheses following this add. So you would run this, and then after running this line of code, you never have to run it again for that particular Julia installation. We already have these things added, the packages that we'll be using today are already added to our environment in Julia Box, so you don't have to run that line of code today. But every time that you run, or every time that you use a given package, you need to use the using keyword to load that package. So in this case, we're going to be using a package called example, which comes from, the package is example.jl. So we say using example, and in this particular case, if we were to look at the source code of the example package, which I provided at the link here, we would see that within the source code there's a function declared called hello, where hello takes a string and then greets the string, or greets the variable that is passed as a string. So now that we have already said using example, we have access to all of the functions from within the example package, which means that we can use this function hello that we would find in the example source code. And there, hello works for us, though we never had to declare it ourselves. Now another fun package to show you is the colors package, which again, we don't have to add here because we're on Julia Box, but we do have to say using colors. And having used colors, we're able to access all of its functions, including this function called distinguishable colors, which gives us as many distinguishable colors as we'd like. Here we're passing the number 100, so we're asking for a palette of 100 different colors, which we see here. And sort of fun thing that I wanted to do with this is to throw it into the rand command. So rand, as I mentioned before, constructs an array of arbitrary dimensions where the dimensions are passed here. So here I'm asking for a randomly populated 3x3 array. By default it's populating with random values between 0 and 1, but if we choose to, we can tell it to populate the array that it creates with something else. So in this case, I'm passing the palette as what rand should draw from to get its random values. So it randomly selects colors to fill a matrix instead of numbers, and we get this colorful random checkerboard.
That's actually pretty cool. I'm kind of surprised that works right out of the box. All right, well.
So there are a few different ways
I'm going to stop there.
plot in
I feel
Julia.
like, plotting we can always look up later. Like, all right, we got all the tools we need to actually run these probabilistic programming languages. So again, so next time I'll do this will be 11 a.m. Eastern Time, United States, next Monday, and we'll dive into Turing.jl. So, I mean, just to kind of summarize again, this is a live stream on applied probabilistic modeling. And what that means is that we're going to look at some of the tools out there for probabilistic modeling and probabilistic machine learning, Bayesian inference, but also look a lot at some of the more DevOps / data engineering tools for that are common in machine learning, and think about use cases for actual Bayesian modeling. The Bayesian, when it comes to Bayesian modeling or probabilistic modeling, whatever you want to call it, there are some of the more useful artifacts you can save. For example, would be things that you generate from sampling from a posterior distribution, and we would be interested in plugging that into some kind of data engineering workflow, because we want to access those posterior artifacts later, because then maybe we want to use them as a prior in some future analysis. And so we'll look at some of these practical, less data science / machine learning, more software engineering / DevOps / ML ops / ETL kinds of tools as well. But we'll specifically in a probabilistic modeling context. So that's the end of the stream for today. I shall post this to the various places, and I hope to see you next time.